Hi everyone. In this video we're going to be going over some problems using conditional proofs. So let's get started. So we have our first problem right here. Now the first thing you might notice, is, well, where are the premises? All I see is a conclusion. There are no premises, at least so far. There's no premises that in this problem. This 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 specific type of, or the specific kind of problem this is called a tautology. So tautology is something that is always true. So what this says is if you have P, then you can get Q then P. So let's take a look at how we prove this tautology. So we're going to use conditional proof again. So just as a reminder, in conditional proofs, you assume the antecedent of the condition of the main operator, which is typically conditional. So we have two conditionals right here. The main operator is this one, and the antecedent would be this P. So we're going to assume P, and we're going to be using an assumption for conditional proof. So now that we have P, well, what can we get? Well, we can get P or not Q. And we do this through one condition. Now that we have P or not Q, we can get not Q or P. And we get this through two commutative. Now that we have not Q or P, we can get Q then P. And we get this through three implication. And so we have the conclusion we're trying to get. If you have P, then you can get Q then P. And we did this through premises 1 through 4, and we used a conditional proof. So again, we didn't have to have any inherent premises that we start off with. Just the way tautology works is if you have this, then you can always get this, right? If you have P, then you can always get Q then P. This problem is just one of the cool little logical problems that you can do. For example, if you have P, then you can assume Q then P, and P becomes the necessary condition of Q. So P is already assumed to be true as it has to be right here. And so if if P were false and it was a necessary condition right here, then you couldn't get Q, and I don't know, you get a contradiction, all this other stuff. So it's pretty cool. This is just a tautology. It's something that's always true. So I thought it would be good to look at. Now that we've finished this problem, let's take a look at a more complicated problem. So the second problem has premises. So it has three premises, and the conclusion is P, then not F and G. So again, we're going to do the same thing. We have one conditional here. The antecedent is P, and that's what we're going to assume. So we're going to start by assuming P, and we're going to do assumption for conditional proof. Now that we have P, let's see what else we can do. Well, in premise 1, I see tautology right there, P or P, so I'm going to get rid of that. I'm going to get P, then M and P, then M and Q, and I did this using one tautology. Let's see. So my next move would be to get M and Q. To get M and Q, and I did this using four, 5 modus ponens. Now I have M and Q. Well, let's see what else I can do. Well, I can't use M yet. Well, actually I can use M. so I will use m. So I'm going to get m through 6 simplification. Now that I have m, I'm going to get not m through 7 double negation. So that I have not m, I'm going to get not f, and I'm going to get not f through 2, 8 modus ponens. So now that I have not f, I mean, I'm eventually going to conjunct not f with g, so my next goal will be to get g. So I'm going to get g by getting q and m. I'm going to get this through 6 commutative. Just let me add a period right here. Get this through 6 commutative, and I'm going to get q. And I'm going to get q through 10 simplification. And now that I have q, I'm going to get g. And I'm going to get g through 3, 11 modus ponens. And now that I have g, I'm going to get not f and g through 9, 12 conjunction. So again, I just want to sort of discuss the virtues, again, of using conditional proofs as opposed to using natural deduction. I mean, as you can see, again, this problem comes a lot simpler than, if we just use natural deduction. I mean, in a lot of cases, we have, just one main operator. In a lot of the premises, we have 0 operators. So no main operators and just, propositions. I mean, the one where we have the most operators is premise 5, which was already listed there in the first place. I mean, we don't add or get rid of any operators, in premise 5. We just get it basically directly from premise 1. So it's really simple. I mean, just using natural deduction, I mean, where would we even start here? I'd have to, I mean, I don't know. I'd probably use tautology, then implication here, then I don't know, maybe use distributive and do like a bunch of other stuff. I mean, I could solve this problem using natural deduction, but it would be a lot harder. And again, if I had this structure, even if I could, use natural deduction, maybe if I wanted a challenge or something, I mean, if I just wanted to solve this problem, I'd use conditional proof, because as you can see from this video and the last video, it's just much simpler to use. So that now we know how to use conditional proofs. In the next video, we'll be looking at solving problems using indirect proofs. See you then.